What if I told you that some exit signs glow without electricity? What if I told you that doctors can see inside the human body without cutting it open? And what if I told you that all of this is possible because of tiny changes inside atoms? These atoms are called isotopes. They are invisible, they are everywhere, and they quietly power medicine, science, safety, and modern technology. In this video, I'm going to clearly explain how isotopes exist, how they behave, and how humans learn to use them in a way that actually makes sense. What an isotope really is. Every atom has a nucleus, and inside that nucleus are protons and neutrons. Protons determine what element an atom is. Neutrons determine which isotope of that element it is. So if you change the number of neutrons in an atom, you do not change the element. You only change the version of that element. That version is called an isotope. Isotopes are atoms of the same element with the same number of protons, but different numbers of neutrons. This small nuclear difference leads to very big consequences. Hydrogen. The simplest example. Hydrogen is the simplest atom in the universe and the best example of isotopes. All hydrogen atoms have one proton, but they can have different numbers of neutrons. Hydrogen 1, also called Protium, has no neutrons. Hydrogen 2, called Deuterium, has one neutron. Hydrogen 3, called Tritium, has two neutrons. All three are hydrogen. They behave like hydrogen chemically, but their nuclei behave very differently. And this is where isotopes become useful. How isotopes come into existence. Isotopes exist through three major processes. First, inside stars. In stars, nuclear reactions constantly create and modify atoms by adding or rearranging neutrons. When stars explode, they spread isotopes across the universe. The atoms in your body were once formed in stars. Second, naturally on Earth. Some isotopes are naturally stable, while others are unstable. Unstable nuclei are unbalanced and eventually release energy to become stable. This process is called radioactive decay. Third, artificially by humans. In nuclear reactors and laboratories, scientists deliberately bombard atoms with particles, forcing them to gain or lose neutrons. This is how many medical and industrial isotopes are produced. Why some isotopes emit radiation. An unstable nucleus cannot remain unstable forever. To reach stability, it releases excess energy. This energy is emitted as alpha particles, beta particles, or gamma rays. This process is not random. It follows strict physical laws. Radiation itself is not evil. The danger comes from uncontrolled or excessive exposure. When radiation is controlled, it becomes one of the most powerful tools in science and medicine. Tritium, the atom that glows by itself. Tritium is a radioactive isotope of hydrogen. It releases low-energy beta particles. These beta particles are very weak. They cannot pass through glass or human skin. When tritium gas is sealed inside a glass tube coated with a phosphor material, the beta particles strike the phosphor and make it glow continuously. No electricity. No batteries. No external power source. This is how self-luminous exit signs work. They glow day and night, even during power failures, and can last for many years. A radioactive isotope quietly becomes a life-saving light. Deuterium. Seeing molecules with NMR. Deuterium is a stable isotope of hydrogen with one neutron. Although it is not radioactive, its nucleus has special magnetic properties. In nuclear magnetic resonance, or NMR, atomic nuclei behave like tiny magnets. When placed in a strong magnetic field, these nuclei align. Radio waves disturb them, and when they relax back, they emit signals. Deuterium is used in NMR because it provides a stable reference signal, helps lock the magnetic field, and does not interfere with normal hydrogen signals. This allows scientists to determine molecular structures, identify chemicals, and study proteins and drugs. In medicine, this same principle is used in MRI scanning. An isotope becomes a window into the molecular world. Isotopes as tracers in medicine. In nuclear medicine, radioisotopes are used as tracers. A small amount of a radioisotope is introduced into the body. It behaves like a normal chemical, but it emits radiation. That radiation escapes the body and is detected by special cameras. A computer then converts the detected radiation into an image. For example, technetium-99m emits gamma rays, has a short half-life, and leaves the body quickly. Doctors use it to study the heart, kidneys, bones, and to detect cancer. Physics becomes diagnosis, following the invisible. Because isotopes emit radiation, scientists can track them. They can follow blood flow, study metabolism, monitor pollution, and observe chemical reactions. The isotope does its normal job, but its radiation reveals its path. Atoms become storytellers. Isotopes as clocks. Carbon-14. Carbon-14 is a radioactive isotope. Living organisms absorb it while alive. When they die, absorption stops. Carbon-14 decays at a constant rate. By measuring how much remains, scientists can calculate the age of fossils, ancient tools, and historical artifacts. Atoms become clocks. Energy from isotopes. Some isotopes release enormous energy when their nuclei split. Uranium-235 is one example. When it undergoes nuclear fission, it releases heat, which produces steam, spins turbines, and generates electricity. A tiny nucleus can power entire cities. Conclusion: isotopes are not just variations of atoms. They are lights that glow without power, eyes that see inside the body, magnets that reveal molecules, clocks that measure history, and engines that power the world. All because of a few extra neutrons inside an atom. The universe is not only around you, it is working quietly inside you. If you learned something from this video, follow, like, and share.